Our first topic of the year is limits. So limits are the base foundation of everything that we will do in this class all year long. We have really three topics of material that we're going to cover. The first is limits, the second is called derivatives, and the third is called integrals, or we sometimes call those antiderivatives. You can't do derivatives or integrals without limits. So we need to have a good, solid base understanding of limits before we can move into anything else. So first off, when we talk about a limit of a function, this right here is the notation that we will be using. Okay? This notation says the limit, that's the LIM part, the limit as x approaches a of f of x is equal to L. So that's how this is read. The limit as x approaches a of f of x is L. Okay? Now, the question then becomes, what is a limit? And a limit is just the y value of a function that we get very, very close to as the x values approach some other number. So as x approaches 2, what does our function get close to? Well, whatever it gets close to is the limit. Now, I'm going to come back and talk about these two questions that I've written here in just a second, but first I want to talk about this little picture that I've drawn on the next page. So I've drawn some random function, y equals f of x in blue there, and I've actually indicated that I've got a hole there on it at x equals a. Okay? And we are wondering, when we think about a limit, what happens to the value of my function as the x values from both sides of a get very, very close to a. So that is this exact thing that I had on the other page. The limit as x approaches a of f of x. And we want to know, what value does our function get close to? Well, it gets close to a value of L, right? That's right there at this number, some real number, L. It could be 2, it could be 7, it could be 1,000, it could be -5. I mean, not in this case because we're above the x-axis, but in general, it could be any positive or negative or 0. It could be a rational number. It could be an irrational number. It just has to be a real number. Okay? So as we get close to a, what y value do we get close to? That's what a limit is. Any questions on the basic idea of that? Okay. Oh no, all of my tools for writing on this are gone. Now they're back. All right, I'm going to draw a really simple function here. Here's the function, and all of my stuff is really hard to draw on the laptop here. It's just, except that my graphs are going to look atrocious. Here's f of x equals x squared. I'm going to ask you, what's the limit as x approaches 2 of f of x squared? Well, as x gets very, very close to 2, y gets close to some number, right? What is that y value that we get very close to? This is the part. Yeah, there we go. 4. That's great. I was going to say, this is the part where you unmute yourself and answer my question. This is great. The limit as x approaches 2 of x squared is 4, right? Because 2 squared is 4. And as my x values from both the left and from the right get very, very close to 2, the y values get very, very close to 4. We're approaching 4. That's the limit. Okay? So there are some more formal definitions of limits, and there's like really formal proofs of limits that we're not going to get into for 2 reasons. 1, because it's not on the AP test, and 2, because we just don't have time. But we do need to think about these 2 questions that I talked about that I didn't talk about over here. That when we talk about a limit, we have to ask ourselves, as x gets close to a, but does not equal a, and that's an important piece of it, as x gets close to that a value, 2 in the one we were just thinking about, but doesn't equal that 2, does the function get close to some real number, L? So if the answer to this is yes, then we move to the second question and we say, can we get our function as close to that L value as we want by picking X values that are very close to A? And if the answer to that is also yes, then we say the limit exists and the limit is L. So if we think about that in the context, and I'm going to do this on Desmos, you're all familiar with Desmos, I hope, right? I was going to do this on Desmos, but apparently Desmos disappeared. There it is. So here's x squared, and here's our point, right? Very close. Trying to get it on there. 2, 4, right? We said the limit as x approaches 2 is 4. So the first question that would be asked if we were looking at this limit of this parabola as x approaches 2 is there some number that y gets very close to? Well, yes, there's some number that y gets close to as x gets close to 2. That number is 4. The second question is, can we get as close to 4 as we want to by picking x values very, very close to 2? So how close do I want to get to 4? I don't know. How about 3.9? Okay. Could I get a value of 3.9, which is very close to 4, by picking an x value that's very close to 2?
Yes.
Yeah, it's pretty easy to do that, right? If I want my y value to equal 3.9, well, I just say 3.9 is equal to x squared, right? And I take a square root. And I can get to 3.9 as long as x is equal to the square root of 3.9, which is a number that's pretty close to 2, right? What if I wanted to get to y equals 3.99? Could I do that?
Yeah.
Yeah, I just pick x to be the square root of 3.99. Right? What if I wanted y to be 3.99999999999999999? Could I get that close if I wanted to?
Yeah.
Yeah, I just got to pick an x value that's really, really, really close to 2, the square root of that 3.999999999999999 value, right? What about from the other side? What if I wanted y to be 4.0000000000000000001? Could I get that y value from that function?
Yes.
Yeah, I just got to pick that x value that's the square root of that, which is exceptionally close to 2, just slightly more than 2. So that's what that second question is asking. Can I get as close as I want to that value by picking a number that's very close to the a value that I'm interested in? Does that make sense to everybody?
Yep.
All right, cool. I think I'm still on Desmos, right? Let's go back to here now. Okay. So what we're going to do is we're going to find a few limits. And to start off with, these limits are going to be really, really, really easy to find, because if the function that we are dealing with is a continuous function, finding its limits is extremely easy. If the function is continuous, the limit is just equal to the value of the function. Right? And that, I hope, should make some sense. Think about any continuous function. In fact, let's think about this continuous function, x squared. Zoom out on it a little bit. What's the limit as x approaches 0? Well, it's 0 squared, it's 0. What's the limit as x approaches 1? Well, it's 1 squared, it's 1. What's the limit as x approaches 5? Well, it's 5 squared, it's 25. It doesn't matter what value I plug into my function, I always get some output that is a real number. And if that's the case, that's telling me that this function is continuous and that the limit is always equal to the value of the function. So let's think about the function 2x minus 3. Is that function always continuous? Yeah, it's just a linear function, right? It exists from negative infinity to infinity. It is continuous for all those values. It's linear. There's no breaks. There's no asymptotes, let's say. There's no discontinuities. There's no holes. So all we have to do is figure out, since this is continuous, because it's linear, the limit as x approaches 4 of this ought to just be 2 times 4 minus 3. And you will find that the first thing that you always want to do with any limit is just take the a value that you have and plug it into the equation. And if you can take that a value and plug it into the equation and get a real number, you're done. We got a real number. We got 5, we're done. The limit as x approaches 4, 2x minus 3 is 5. Good or no?
Good.
Yes.
This should be pretty straightforward, I hope. What about the limit as x approaches -3 of x squared plus 1? Is this function continuous for all real numbers?
Yes.
Yep, which means it's continuous at -3, which means if I plug in -3 to this, I ought to just get a real number, and that should be my answer. What's -3 squared plus 1?
10.
10. Perfect. Easy. What about the square root of x plus 2? Is that continuous for all real numbers?
Yes.
Really? Like, what about -7?
No.
Oh.
No. It's not continuous for all real numbers. What's the domain of this?
-2 to infinity.
-2 to infinity, inclusive on the -2, right? With a bracket. -2 to infinity. Is it continuous for all of those numbers?
Yeah.
Yeah, it's continuous on its entire domain, which is good. So we can just plug this number in, the square root of 7 plus 2, which is the square root of 9 or 3. And make sure that when you take your square roots, if there's not a negative sign written in front of it, that your answer is just the +3. Don't give me plus or minus 3. The only time you would get plus or minus 3 is if you were solving an equation like x squared equals 9. Then x would be plus or minus 3. But the square root of 9 is just 3. Everybody good there? So the first thing that you will do every single time that you are trying to find a limit is take the a value and plug it in. Just plug it in, plug it in. You get a number, you're done. Couldn't be any easier than that. Plug in the a value, get a number, done. Any questions on that? Okay, what's the first thing you will always do with a limit?
Plug in the a value.
Plug in the a value. All right. So here is a function, 2x plus 1. We're going to find 3 limits. This should be the easiest thing that you will do this entire year and that you've ever done in any math class ever in the history of your entire existence. The limit as x approaches 3 of f of x. What's the first thing you do? Plug in
the a value.
2 times 3 plus 1 gives you 7. And we'll note that if we look at the value at x equals 3, it is 7. What should we do with this one?
Plug in -3.
Plug in that -3a value. What does that give you? -5. There's -3, -5. It's just the point on the function because it's a continuous function. Plug in 0. What do you get? 1. At 0, it's 1. It couldn't be any simpler. Everybody good?
Yes.
All right. I promise you this is the last one of these that I'm going to have you do. Here's your function, x plus 2. What's the limit as x approaches 1?
3.
3. Spectacular. It's just the value of that point. Now, we're going to make things get a little bit more complicated. Here's our new function, g of x. G of x is equal to x squared plus x minus 2 over x minus 1. What's the first thing we should do?
Plug in a.
Plug in our a value. That gives us 1 squared, which is 1, plus 1, minus 2, divided by 1, minus 1. And what does that come out to be?
Undefined.
It's 0 over 0. Now, I heard somebody say that that is undefined. That's sort of true, right? You can't do 0 divided by 0, but this has a special name for it. The special name for this is, it is indeterminate. So when we get to calculus now, we are going to make a distinction between when something is undefined and when something is indeterminate. Something is undefined if you have 7 divided by 0. That's undefined because you can't divide by 0, right? 3 divided by 0, undefined. But 0 divided by 0 is a special case of being undefined where it's indeterminate. And whenever a limit comes out to be indeterminate, it means we got to do some more work to deal with it. So we've got x squared plus x minus 2 over x minus 1. Well, we would probably note that the reason that there's a hole in the graph here at x equals 1 is because if I factor this, the numerator becomes x minus 1 and x plus 2. Would you all agree with that?
Yes.
And the x minus 1s cancel, right? The x minus 1s canceling out gives us this hole at x equals 1. Okay. So effectively, this function is just the x plus 2 function, just like we had right here, except with a hole at x equals 1. So then the question becomes, what is the limit as x approaches 1? Well, let's ask ourselves these questions that we had from the very first page. As x approaches 1, is there a y value that we get very close to?
Yes.
Gets pretty close to 3.
It gets pretty close to 3, doesn't it? Right? Can we get as close to 3 as we want to by picking x values that are closer and closer and closer to 1?
Yes.
Yeah. If I wanted to get 2.999999999, there is an x value that will give me that. It's very close to 1, but it's not quite 1, right? So it meets both of the criteria. It says that we do get very close to a value, we get very close to 3, and we can get as close to 3 as we want by picking numbers very close to 1. So what does this limit equal?
Three.
Should be 3. And we'll note that even though our function is undefined at x equals 1, right, it's an indeterminate limit there, the function doesn't exist at x equals 1. There still is a limit there. That's okay. And the whole idea behind calculus and limits is that we are looking at not what happens at the point x equals 1, but we are looking at what happens on the very, very tiny interval approaching 1, some very small, tiny interval that surrounds 1, but not at 1. We don't care what happens at 1. We're only caring about what happens as we approach 1. Good or no?
Good.
All right. Let's take a look at another one here. We've got h of x is equal to x squared plus x minus 2 over x minus 1 when x is not 1, and h of x equals 2 when x is 1. Is the function continuous for all real numbers? The answer there should be no. This function is not continuous for all real numbers, right? It has a discontinuity at x equals 1. The function is still defined at x equals 1, but the function is not continuous. Right? So since it's not continuous, that means we can't just plug it in and get an answer. So we have to ask ourselves those same two questions. First question is there a number that we are approaching that we're getting close to as x approaches 1?
Yes, it's
What is
still 3.
We're still getting close to 3. Can we get as close to 3 as we want to by picking numbers closer and closer to 1?
Yeah.
Yeah. So what's this limit?
It's still 3.
Still 3. Okay. Like I was saying on the last slide, it doesn't matter what happens at x equals 1. All that matters is what happens as we get very, very close to x equals 1. And that's the whole idea of limits, is what's happening very close to that a value. So we would note that the functions that we just dealt with, f of x, g of x, and h of x, were all very similar functions, right? Except that f of x was continuous all the way through. G of x just had a hole, and h of x had the hole, but then had another point at x equals 1 at a different value. And they all had the same limits. The limit was 3 for each of them, but for one of them, the value of the function was 3. For one of them, the function didn't exist. And for one of them, the value of the function was completely different than what the limit was. And this is completely okay. All 3 of those situations can happen and will happen, right? The limit can equal the value of the function. The limit can exist when the function doesn't exist. And the limit can be something different than the value of the function. Everybody good or no?
Good.
Good.
Perfect. All right. Let's move a little bit forward here and take a look at some other function we've got. Sine x over x. We want the limit as x approaches 0 of that. So plug in 0. What do you get? What's the sine of 0?
Zero.
0.
0.
We have 0 over 0, which means that this is indeterminate. Sorry about my atrocious handwriting. This is indeterminate, which means that anytime you have an indeterminate limit, you're going to have to do some other work to find that value. Now, in this particular case, the work that we're going to do to find that limit is beyond the scope of what we learned so far. So what we're going to do is we're going to look at this graph and say, what does it look like that limit is?
1.
Sure looks like it's 1, doesn't it? We're going to say equals 1 question mark, just based on our observation of the graph. It sure looks like it could be 1. And I'll tell you, it is 1. And one thing that you sometimes might end up doing on the AP test is taking a guess at what the limit of something is just by looking at its graph and zooming in on it. And we're going to talk more about how to do that using your graphing calculator, but I'm going to do it on Desmos. And if you zoom in, and it doesn't look like anything weird is happening here at x equals 0, other than the fact that we know there's a hole there because it's 0 over 0. Desmos doesn't ever show the holes. Nothing weird is happening. It's not like shooting up to an asymptote or shooting down to an asymptote on one side, right? It looks like just a good old normal little function there as x approaches 0. If there's nothing weird happening with the graph, we can assume that that limit is whatever value it looks like it should be. We'll assume that it's 1, but that's not a real solid way of finding your limit and being certain of it. Okay? So we could always look on a smaller interval and something weird might be happening on that smaller interval. Now on this one, there's not, but for other ones, there might be. And so you can use a graph to estimate a limit, but remember that it's just an estimate. It's just a guess, that it's not for certain. All right, we're going to do a couple more problems here, and then we're going to call it a day. So you don't need to graph this on your graphing calculator. It's fine. This is the function x cubed minus 2x squared over 3x minus 6. And we want the limit as x approaches 2 of f of x. And so clearly, I've drawn that there's a hole on there. There's a hole at x equals 2 on this. If you plug in 2, what do you get? You get 8 minus 2 times 4 over 6 minus 6. So you get 0 over 0. You get indeterminate. It tells us that there's a hole at x equals 2. Any good guesses just looking at the graph of what that answer should be?
Around 1.5.
Sorry, say that again. Around what?
Around 1.5, maybe smaller.
Okay, 1.5-ish, maybe. Yeah, it looks like it's around there, maybe a little lower than that, right? You said it looks, yeah, it looks like it's a little lower than 1.5. Right? Could have a decent estimate of it on that. Anybody else have a different guess on what it might be?
Like 1 1/3.
1 1/3, maybe. Yeah, maybe it's possible, right? I hate 1 1/3. I much prefer 4/3, but that's fine. Try to go with improper fractions whenever you can. Yeah, I mean, it could be that, maybe 1 1/4, 1 1/3, a little less than 1.5, 1.4, who knows? If we were to graph it and really zoom in on it, what do we have? We had x cubed, what was it? X cubed minus 2x squared, is that right?
Divided by 3x minus 6.
Perfect, thank you. So if we zoom in on 2, just a little bit. So here's 2, and it looks like, well, yeah, there's 1.5, so it's definitely less than 1.5. 1 1/4 would be right here, so it's definitely more than that. So 4/3 or 1 1/3 seems like a good guess. And we can look, oh, at 1.999, the value of our function is 1.332. And at 2, like we said, it's undefined. And then at 2.003, it's 1.3373. So what does it look like it's very close to with a little zooming in?
4/3.
It does look like it came out to be very close to this value, right? So can we prove that to be the case? Because just estimating it from the graph is not good enough. How can we prove that algebraically, that limit that when we plugged in and got 0 over 0 is actually 4/3 or 1 1/3?
Factor it out.
Yeah, that's exactly what we'll do. And there's other ways to do it. But the first method we're going to talk about is by factoring. So I can take an x squared out of the numerator, which gives me x squared times x minus 2. And I'll take a 3 out of the denominator, and we'll get 3 times x minus 2. And can I cancel out these x minus 2's?
Yes, I think so.
Yes, you think so. Yeah, you've been taught before that you can, right? And whoever you had for like integrated 3 or pre-cal was like, yeah, cancel those out, right?
Yeah.
Why do you cancel them out? Because anything divided by itself is
1.
1. Well, that's not entirely true. 0 divided by 0 is not 1, is it? 0 divided by 0 is indeterminate. So as long as x minus 2 is not equal 0, then we can cancel those out. Well, what x value makes x minus 2 equal 0?
2.
2.
2. So as long as x can't equal 2, well, our limit is x approaching 2. So what does that tell us? What are we interested in? If it's a limit as x approaches 2, we are interested in what happens to this function when
Approaching 2.
When x is approaching 2, when x is very, 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 very close to 2. Are we interested in what's happening to this function when x equals 2?
No.
No, we don't care about that. We only care about what's happening when x approaches 2. So in this limit, is x ever going to equal 2?
No.
No. So as long as x minus 2 is not 0 or x is not 2, those will cancel. And we can say that this is equivalent to the limit as x approaches 2 of x squared over 3. Right? Because when I plug in 1.999999999999999 up here, then this is a number divided by that same number, negative 0.00000001 divided by itself, which is just 1, and it cancels. So now we have a new limit that we're looking at, the limit as x approaches 2 of x squared over 3. This one, we try, the first thing we'll try with our new limit that's equivalent to this limit is plugging in the x equals 2 value to get 2 squared over 3, which is the 4/3 that we were hoping it would be. Good or no?
Yep.
Okay. You don't need to write out all of this. You can just cancel it out, write this, and then cancel it, and write this, and evaluate. Okay. All right. Let's do another one. We just, I did that on the last page. All right, let's do another one. Let's find the limit as x approaches 2 of f of x, with f of x equal to 2x squared minus 5x plus 2 over 5x squared minus 7x minus 6. What's the first thing we should do?
Plug in A.
Plug in our a value, plug in 2. So we got 2 times 2 squared, that's 8, minus 5 times 2 is 10, plus 2. And then 5 times 2 squared, that'd be 20, minus 14 minus 6. The numerator comes out to be
0.
0. The denominator comes out to be
Also 0.
also 0. So we are indeterminate. If this was 0 over 2, well, 0 over 2 is just 0, right? We'd be done. If this was 2 divided by 0, that'd be undefined. We would say this limit doesn't exist. We'll get to those later on. But if it's 0 over 0, we do the extra work. So we'll do this extra work of factoring. Hopefully both those factor. Now, we should be clued into what one of the factors should be in both the numerator and the denominator, because we know if we plug in 2 to both of them, we get 0. So what do you think one of the factors should be?
X minus 2.
Yep. And what does that make the other factor of the numerator? It's going to have a 2x, right, to give us a 2x squared. And then we need a plus 2, so that'll be a minus 1. Does that work out for the minus 5x? It gives us a minus x and a minus 4x. So looks like it. And then the x minus 2 will have to get multiplied by a 5x to give us a 5x squared, and a plus 3 to give us a minus 6. And we'll check these outside and inside terms. Positive 3x and negative 10x definitely gives us negative 7x. So what can we do now, since x does not equal 2, x is approaching 2, we can cancel those x minus 2's, get a new limit. The limit as x approaches 2 of 2x minus 1 over 5x plus 3. Note that I'm still writing the limit as x approaches 2 every time until I start to evaluate. Now that I've evaluated, plugged in the 2, I don't write the limit anymore. 4 minus 1 is 3. 10 plus 3 is 13. Our limit is 3/13. Good or no?
Good.
Good.
Perfect. That is it for today.